Hi guys, so in today's video we're going to do Newton's second law in terms of momentum. So if you still remember correctly, in our first videos we did a revision where we covered Newton's second law, Newton's first law, Newton's third law, Newton uh, universal of gravitation. So we also revised Newton's second law, where we said the F net is equals to ma, which is a mass multiplied by acceleration. So this is what we revised, and this is a Newton's second law, that when a net force is applied on an object, the object will accelerate in the direction of the F net, and also that the acceleration is directly proportional to the force and inversely proportional to the mass. So wanna check what's the relationship between this Newton second law and momentum. So when an object accelerates, will increase or decrease the velocity? We know that. So if object increase or decrease the velocity, that means any object has a mass. So if object is increasing or decreasing the velocity, or if object is moving with a constant velocity, that means that object has a momentum. So momentum can help us to state Newton's second law. So we're going to state Newton's second law again in terms of momentum. So now we just have to restate the Newton's second law using the momentum, because now we learn the momentum. So let's start with acceleration. So what's the acceleration? Or let's start with the momentum, so it's gonna be easy. We said the momentum, it's mass multiplied by a velocity, and we said that the change in momentum is given by the mass multiplied by velocity final minus mass multiplied by velocity initial. This is the change in momentum. Those are the concepts that we covered. So now let's see how we can relate the momentum with Newton's second law. So we know that acceleration, let's take it from here. Acceleration, by definition, when we're covering the concepts, it's a change in velocity over time. So it's a change is given by the change in velocity over the change in time. So it's a v final minus v initial divided by the change in time. So this is what we said about acceleration. So therefore we can take it further by saying that F net is the same as mass multiplied by, we substitute acceleration by this one, which is velocity final minus velocity initial. Velocity final minus velocity initial over time, which this is the acceleration, guys. This is the same as this one, is acceleration. So after this, we can multiply out what's inside the brackets. So going to say this is the same as mass multiplied by velocity final minus mass multiplied by velocity initial over change in time. So you can spot something here. We have this mass multiplied by velocity final minus mass multiplied by velocity initial, which is the same as this one here. It's the same as this one. So we can conclude by saying that this is F net is equals to the change in momentum over time. So we are going to state Newton's second law now in terms of this one, in terms of this formula. So what we can conclude with this one, can say that Newton's second law, was stating Newton's second law now again using this one. So we can say that the net force applied net force F net applied on an object object is equal to the rate of change of momentum. So we can see now here that the F net applied on an object is equal to the rate of change of momentum, or is equal to the momentum over time. So that's how you can state Newton's second law in terms of momentum. The F net applied on an object is equal to the rate of change of momentum. You can see here. So that's how you can state Newton's second law in terms of momentum. So now let's move on to example. I'm going to do one example for this one, for Newton's second law in terms of momentum. So here we have this example. It says that sun L has a mass of 40 kg. So mass is 40 kg. Has a mass of 40 kg and is sitting inside a 20 kg cart. So we have a 20 kg cart. Sanel's friends pulled the cart with a force of 500 Newton at an angle of 20 degrees. So here, let's say here you have this is the cart, then inside the cart, Zanel is here inside, and then the friends are pulling this with an angle of 20. So the friends are pulling with an angle of 20. At an angle of 20, and then they're pulling with 500. There's going to be 500 here. 500 Newton. At an angle of 20 to the horizontal. Using a light rope, the cart experiences a friction force of 300 Newton. So the friction force for this one is 300. It's 300 Newton. So first question says, calculate the net horizontal force acting on the cart. So one, the net horizontal force. So how to calculate that? So let's write everything we're given. The mass of Sanel, it's 20 kg. The mass of the cart, it's 40. So this one is 40. This is 20 kg. And then the force applied, F applied, it's given. It's 500 Newton, and the frictional force is also given, is 300 Newton. So we want to calculate the horizontal force, the net horizontal force. And remember that if we can draw a free body diagram, let's start with a free body diagram. Learned how to do that in grade E11. So if you don't know, just going to show you how to draw a free body diagram. So a free body diagram, we put a dot here. Then after that, this is going to be the Zanel. It's a system. It's a Zanel and the cart system. Then after that, you do this. This is the F applied, which is 500. Let's just write FA applied, which is 500. Then here you have a frictional force going this way, which is F friction, and then you have a weight, this weight, and you have a normal force. So the weight and the normal force, they balance each other, they're equal. So therefore the cart is not moving up and down, it's moving horizontal. So therefore that means the horizontal forces are not balanced. So we want to calculate the net force. So if the cart is going this way, that means also the F net is going this way. The F net. Because Newton's second law, it states that the object will accelerate in the direction of the F net. So if it's going this way, therefore the net force is going that way also. Okay, so here we want to calculate the horizontal force of this. So you can see from this one that this angle here, this small angle here, it's 20. We're given that small angle. So if this small angle is given is 20 and we want the horizontal force from that, So if that angle there, it's 20 and we want the horizontal force, we can just use the trigonometric ratio. So if you can check, we have a triangle like this. This is the f that we are given, and then we want this one, which is this the f axis horizontal. And then we also have this one that's going up is the fy. So, and we have this here, we're going to call that theta. So you can see that we can use cos. We can use a cos because this angle is adjacent. So we know that cos of theta is equals to the adjacent side, which is the fx over hypotenuse, which is f. So the fx tend to be f cos of theta. So that f is the one that we are given, and then cos of theta, the theta said 20 is that 20 that we are given, 20 degrees that we are given. So we're just going to complete it here. So let's check how can we complete it. So that, and this is, if it's going this way, these forces are going in opposite direction. So we can just say the f net horizontal, it's given by, because you can see that we have the one that's going this way, so it's going to be the fx. We're going to add the horizontal forces plus inside, since this one is going that way, the frictional force, we're going to put minus the f friction. So because it's going in opposite direction, so it's going to be minus. But if they were going in the same direction, we just add them. So if they are going in opposite direction, you subtract the fx by f friction. So after this, we're going to substitute the fx, and fx we know that is f cos of theta minus the frictional force. So f were given, which is 500. So just going to say 500, the cos of 20, the cos of 20 minus 300. That's what we are given. And then 500, it's 500, the cos of 20 minus 300. Get 169.85 Newton. So this is the horizontal force. It's a F net horizontal. So this is the F net horizontal. So let's move on to next question. So next one says, so the next one says, calculate the change in the car's momentum if Sun and L's friends apply the force for 10 seconds. So now we have a change in time. So the change in time is given by what? Change in time is given by 10 seconds. And then the F net, we calculated that it's 169.85 Newton. So that's F net. So we can calculate the change in momentum. Remember that we said that the F net is equal to the change in momentum divided by the change in time. So we can just say change in momentum. The change in momentum P, it's given by F net multiplied by change in time. Change in time. You can see that. So just going to substitute. The change in momentum P is going to be F net, which is 169.85 multiplied by change in time, which is 10 seconds. So the change in momentum P is going to be 169.85 times 10. So it's a 1698.5 kg meter per second. So in which direction? Since it's positive, that means it's going to the direction of a net force. So since our net force was going this way, so it's to the right, to the right, the right. Because our net force was going in this way. So also this one is going to go to the direction of net force. Okay, thanks for watching my video. See you next time.